This video will be a review of solutions and concentration, including units. So, starting off, vocab-wise, a solution is just a homogeneous or a homogeneous, however you want to say that, mixture of two or more things. So we could have 47 things mixed together. As long as they're evenly mixed, it's a solution. And it could be solids, liquids, gases, or a combination of all of those. We can have a solution between just gases, we can have a solution between gases and liquids, liquids and liquids, solids and liquids, whatever. Still vocab-wise, in a solution, the one substance, the one component that there is the most of in that solution is called the solvent. So where it says major species in a solution, that's the one that there are the most of. So if there are 47 things, there is one solvent, only one thing that there's the most of. Then the 46 other things would be the solutes. The solutes are the ones that are not the most abundant in the mixture. There can be multiple solutes, but there will only be ever one solvent. So when we're dealing with solutions, we have to talk about certain things that dissolve, whether or not they are electrolytes. So a non-electrolyte is something that when it dissolves in water, so that's our aqueous solution, just means that the solvent is water. A non-electrolyte is a solute that when it dissolves in water doesn't dissociate, does not break down into smaller pieces, stays the entire molecule. So any soluble organic compounds like ethanol, when it dissolves in water, it stays its entire compound, does not break apart into pieces. Electrolytes are things that when they dissolve in water do dissociate into their individual ions. So we have two different categories of electrolytes. Strong electrolytes, which are pretty much 100% dissociated. You put them in water, they will all break apart into their cation positive charge, anion negative charge, and stay that way. I can't say for sure 100% because we'll talk later in the semester about how what actually happens with this, but they dissociate as much as they can. So these are our soluble ionic compounds. So if you remember the beautiful solubility rules from Gen Chem 1, anything that was considered soluble from those solubility rules, that's a strong electrolyte. And then any of the strong acids or strong bases, those are all strong electrolytes, dissociate completely. Weak electrolytes, they are under the category of an electrolyte because they do dissociate, but only a certain percentage of the molecules dissociate, and that percentage is much less than like 99. Usually we're talking less than 10% of the molecules dissociate. So insoluble ionic compounds are considered weak electrolytes because although the solubility rules in Gen Chem 1 said they were insoluble, they didn't dissolve. They actually go to equilibrium dissociating, so a small fraction of them do dissociate, and then all the weak acids and weak bases. To be considered an acid, if we're talking the Bronsted-Lowry definition, it has to donate a proton or an H+, and a base has to accept an H+, so there has to be some sort of ions going on with those, but again, usually these are like 2 to 10% of these molecules dissociate. So like HF is on here. So we'll go with 90% of the HF molecules when they're dissolved in water stay the hydrogen bonded to the fluorine, but less than 10% of them dissociate into H+ and F-. So looking at the units of concentration, the one that chemists use most often is molarity, which is abbreviated with a capital M. And the definition of molarity is the moles of the solute divided by the liters of the solution. So solution is total. So that's the volume of the solutes and the solvent. So if you have more than just two things mixed together, let's say you have multiple solutes, you can have a molarity of each of the solutes in the mixture. When you see this, sometimes they'll just take the solute that they're looking at and then put brackets around it, and that is signifying the molarity. So the example of NaCl in brackets, so if someone says NaCl is shown NaCl in brackets, they're saying whatever it's equal to is the actual molarity. That's implied units. Molarity, although it's the most commonly used unit of concentration, that's mostly due to convenience in the lab because we can easily get from grams to moles, and of the solute, and we can get grams from our balances. The liters of the solution, so the volume of the total, just converted to liters, our lovely volumetric flasks are set at certain volumes that we just mix together the components until they get to that volume. So it's very easy for us to know the final volume of the solution because of balances and volumetric flasks. But volumes of liquids are temperature dependent. You increase the temperature, they expand. You decrease the temperature, they get smaller. So molarity is actually temperature dependent. And really, our volumetric flasks are temperature dependent. All of them are set that, let's say we have a 100 milliliter volumetric flask, it's really only 100.0 milliliters at the temperature that is stamped on the piece of glassware, which is usually 20 degrees Celsius. So there's our definition, moles of solute divided by liters of solution. Let's do an example actually calculating. Okay, so this is, again, the way that usually we're making solutions in the lab. We have a solid. In this case, the solid is the potassium hydrogen phthalate that we call KHP. And then we transfer it to a volumetric flask, add water to dissolve it, and then add the water up to the line on the volumetric flask. So in this case, it was measured out 2.4930 grams of potassium hydrogen phthalate, and we put that into a 250 milliliter volumetric flask, and then water was added to the line. It was capped, it was inverted, and mixed. So again, we're doing molarity, so that's beautiful. Moles of solute, which in this case is going to be KHP, divided by liters of solution, which will be the total. Okay, so what we need to do is convert our grams of KHP into moles of KHP, so we're just going to be doing dimensional analysis on that. So 2.4930 grams of KHP. So we'll use the molar mass of KHP, which was given in the problem. So there are 204.22 grams of KHP in 1 mole. So this would get me my grams, or I convert my grams of KHP into moles of KHP. So that could be my numerator in the equation. But I like to do these dimensional analysis calculations all in one long row. I don't like to break it apart. So right now I have moles of KHP on the top. If I can get liters of the solution in the denominator, then that's the definition of molarity. So I can either, what I like to do is just put the volume down here. Now the volume given in the problem was 250.0 milliliters, but we can't leave it in milliliters. That's not the definition of molarity, so we have to convert that to liters. If you choose to convert milliliters to liters in your head, there's nothing wrong with that, but there are 1,000 milliliters in 1 liter. So looking at units, cancel the milliliters, well, sort of. The only units left are moles of KHP on top, and then liters of solution on the bottom. So I just plug this into my calculator, and I get 0.04883. The unit is capital M for molarity. So molarity is the most common concentration unit, but there are many other ones. You would have learned these in Gen Chem 2. Molality, which is abbreviated with a lowercase m, is moles of solute divided by kilograms of solvent. So molarity, similar word, but different. They both have moles of solute in the numerator, but their denominators are different. Remember, with molarity, it was liters of solution, which is total, and this one is kilograms of solvent, which is the thing that there is the most of. So really, molality is the concentration unit we should use, because no matter what you do to the temperature, the molality value doesn't change, because this is based on mass, and the mass doesn't change based on temperature. Volumes do, but there are no volumes here. Unfortunately, this is not as easy to get the measurements for in the lab, because like you're making a mixture, you don't normally measure out the mass of the water that you're going to mix something with, because usually, in our case, water is our solvent, plus our balances can only go to like 200 grams, so we would run into issues with this. So it's great in theory, but in reality it's kind of hard to do in the lab. Some other very common units are percent composition. So we either have weight percent or volume percent. It's basically just like any other percent. If it's weight percent, though, the units that you're using are grams, and if it's volume percent, the units can be any volume unit, but for us usually it would be milliliters. So it's just the mass of the solute you're looking at divided by the total mass, and then times 100 to make it a percentage, and with volume, the volume of the solute divided by the total volume times 100. A lot of solutions that you buy at the store, think like cleaning supplies or laundry detergent or anything, those are usually in one of these two concentration units if you actually look at the container, and a lot of times they're volume percent just because they're liquids, so that's the easiest thing. If it just says percent and it doesn't tell you if it's weight percent or volume percent, it's assumed that it's weight percent. So unless you're told otherwise, a percentage is going to be weight percent. If it's volume percent, it really needs to be shown like the VOL in there. And then parts per million ppm and parts per billion ppb. These concentration units are really only used on very dilute substances, so when we have very little of something. The way that their definition is always shown looks very similar to percent composition from the last slide. You know, mass of the solute or whatever divided by mass of the total, but instead of times 100, it's times a million for parts per million and times a billion for parts per billion. That should be a B. Sorry. Nope, it does not want to be my friend today. Let's see, pen. That is beautiful. There's parts per billion right there. Yeah, okay. So those are the definitions you're usually given, but as long as we're dealing with an aqueous solution, the units that are most useful and easiest to get in the lab are actually not using that. It's actually parts per million is if you take the milligrams of the solute divided by the liters of the solution, that gets you parts per million. And for parts per billion, micrograms. So this is easier because the liters of the solution we can get from the volumetric flask that we're making the solution in. Milligrams, we can measure out the grams on the balance, convert it to milligrams. Micrograms, we can measure out grams on the balance, convert it to micrograms. This only works, these two things only work when the solvent is water, and that's due to the density of water being pretty much 1 gram per milliliter. So let's do an example calculation with our parts per million. So we've got 0.4530 grams of calcium chloride was measured and made to a solution with water using a 500 milliliter volumetric flask, so the total volume is the 500.0 milliliters. We want to figure out the parts per million of just the calcium ion in the solution, and in this case calcium chloride is a strong electrolyte, so when it dissociates it's going to break into calcium ion, that's a plus, and 2 chloride ions. So we don't really care about the chloride part, we just want to know the parts per million of calcium. So since this is using water, we can get parts per million by getting the milligrams of calcium on top and the liters of the solution on the bottom. And we do not multiply that by a million or a billion. Okay, so the issue we have here, we've definitely got the volume in milliliters, and we can convert that to liters easily, but the mass that I have, that's the mass of calcium chloride, and I want just the mass of calcium. So I have to do a little bit of dimensional analysis here. So I'm going to start with the 0.4530 grams of calcium chloride and just do some dimensional analysis to convert that into milligrams of calcium. So I'm going to start by using the molar mass of calcium chloride. So up there it was given in the parentheses 110.9834 grams in 1 mole calcium chloride. So for every 1 calcium chloride, we're really only interested in the calcium, but there's only 1 calcium. So I want to convert that into, well, grams and then eventually milligrams. So the molar mass of calcium is 40.078 grams. 1 gram has 1,000 milligrams. So this would cancel out grams of calcium chloride, grams of calcium chloride, moles of calcium chloride, moles of calcium chloride, moles of calcium, moles of calcium, grams of calcium, grams of calcium. So we have milligrams of calcium on top. If I can divide that by liters, so this time I'm just going to do the milliliters to liters conversion in my head. So 500.0 milliliters, I divide that by 1,000 in my head, so 0.5000 liters. Oh. So the only units left are milligrams on top and liters on the bottom. So my final answer is, sorry, bad, not that, 327.2 ppm. Okay. So that was even an added twist onto this because I didn't want the ppm of calcium chloride, but I wanted the ppm of just 1 ion. That's going to come up in lab, so don't be surprised if something like this appears. Okay, so when we're dealing with solutions, like I said, we can make solutions by measuring out the grams and then putting them into a volumetric flask, but another way to make solution is to do a dilution, which is to take a stronger version of the chemical that you're trying to make and add water to it. So the M1V1, M2V2 calculation is how we can do the math for dilution problems. So let's just do an example of this. So the M1V1, what I'm saying is 1 and 2, our textbook uses concentrated and dilute. But really what we're doing is we would take the concentration of the strong solution that has already been made, put how many milliliters of that you used, and then this would be the concentration of the new weaker solution that you made, and this is how much of that weaker solution that you used. The volumes can be in any unit as long as they're the same, and technically the M's stand for molarity, but they can be also in any concentration unit that you need as long as they're the same on both sides. Like you couldn't put molarity on one side and parts per million on the other, but you could do parts per million, or molality, molality. It doesn't matter at the unit, you can still use the M1V1, M2V2. So this one we're sticking easy with the units that we're using are molarity, but we're trying to make looks like 1.127 molar sodium hydroxide solution. So we're trying to figure out how much of the 7.51 molar sodium hydroxide solution that's ready and sitting in front of me I need to use that to make 100 milliliters of a 1.127 molarity sodium hydroxide solution. So we're using the strong one to make the weak one. So we need to figure that out. So I'm going to call the 1's my concentrated side and the 2's my diluted side. The concentrated side is the one with the highest molarity. So 7.51 is my highest molarity. So if I'm going to do M1 V1 equals M2 V2, then 7.51 molarity times the volume that I don't know will get me 1.127 molarity, 100.0 milliliters. So now I just have to do rearranging. And V1, I get 15.0 milliliters. So what this is telling me, I would need to get the pipettes out to transfer 15.0 milliliters of this 7.51 molar sodium hydroxide solution, put those 15 milliliters into a 100 milliliter volumetric flask, fill it up to the line with water, invert it, and we're good to go. So just to prove that we can do this with any units, we've got another dilution calculation, only this time we're looking at concentration in parts per billion, ppb. So we're just using a very weak solution. So this time we're trying to figure out what the concentration would be when we make this solution. So if we take 8 milliliters, 8.00 milliliters of a 1.451 parts per billion solution of zinc ion, add that to a 1 liter volumetric flask, I want to know what is the concentration of that new solution that is the 1 liter. So we're still going to be using M1, V1, M2, V2, and I'm still going to make my one side my more concentrated side and my two side my weaker side. So my more concentrated side is going to be the 1.451 ppb, and we're using 8.00 milliliters of it. We don't know what the new molarity will be, but we're making 1 liter. So if I put 1 liter in here, the problem we run into, I said the units have to be the same on both sides. So I have milliliters on one side, I can't have liters on the other. So 1 liter is the same thing as 1,000 milliliters. So I'm plugging that in so that way my units are the same on both sides. So I just have to do division, my milliliters will cancel, and I will end up with 0.0116 as my M2, and the units for that will be parts per billion. We're going to be using M1, V1, M2, V2 pretty much every week in the lab. So if this is something that you're still not feeling comfortable with, I would definitely come see me because it's not going anywhere and we'll be using it the entire semester. All right.